All right, let me just have a little fireside chat before we really formally begin on the next homework. So how many of you got a bit of a headache over the first homework? Right? I mean, it was a bit of a, I think that you will find, nobody's ever accused me of having my homework being easy, but I think that you'll find it gets a little bit easier as we go along. This one should not be so bad. The first one, let G be a finite group. So it's a group, finitely many elements in it. Show any element of G has finite order. My hint to you there is just take an element X and G and just keep combining it with self. X times X, X times X times X, and keep going and see what happens. Show that any group of exponent 2 is abelian. Anybody remember, what does it mean for a group to be of exponent 2? I guess we really need to kind of understand what in the world I'm saying here. It means the order of every element in the group divides 2. Right? So it's the smallest one. So in other words, what it means for a group to be of exponent 2 is every element in that group has order 2 or 1. And the only element that has order 1 is the identity. So everything in here except the identity has order 2. Any group of exponent 2 is abelian. There are infinite groups that have exponent 2, but they're all abelian. This problem is no longer true if you replace the number 2 with the number 3, as a matter of fact. Number 3, the goal of this problem is to show that any finite group generated by 2 elements of order 2 is dihedral. Suppose that you have G and it's generated by X and Y, both elements of order 2. It will also assume that X and Y are not inverses of each other. Assuming the order of G is finite, what can you say about the order of the element X, Y, and G? I'm not asking for anything deep here. In fact, you might look back at problem number 1 to help you out there. Number B, show that the group generated by X and Y is the same as the group generated by X, Y, and Y. And we'll talk about what generated by means in a moment. We've mentioned it in passing. And show this group generated by X and Y to demonstrate exactly. And finally, this might take you a little bit back to linear algebra. How many of you have heard the word field before? Probably if you're in linear algebra, you've heard this. A field is sort of a generalization of the real numbers, right? The real numbers, you can add things, you can multiply things, and actually under addition, a field is an abelian group. And under multiplication, it's an abelian group if you throw out 0. So if you throw out the real number 0, everything has an inverse. So let F be a finite field. You can assume that such an animal exists. It turns out that there are finite fields. We've seen some examples actually. Z mod P, where P is a prime, is actually a finite field because all non-zero elements had a multiplicative inverse. But it turns out that for any prime P and any natural number N, there is a finite field of order P to the N. This is very important in things like coding theory. Let T and F be the collection of N by N upper triangular matrices over F that are invertible. And by invertible here we mean non-zero determinant. Prove that T and F is a group and count the number of elements in T and F. You may use any convenient fact from linear algebra that just quote them, including the fact that the inverse of an upper triangular matrix is an upper triangular matrix. Did you all see that in linear algebra, that if you have an upper triangular matrix, it's invertible, it's inverse, it's also an upper triangle. So anyway, I think that you will find this perhaps less taxing than last week. Any questions? So let's look at this. Okay, so the last time we were talking about, I showed you how to do these computations. Maybe it would help to kind of review this a bit. This is an element of S6, and in fact, it's an element of Sn for any n bigger than 6. Let's find what this sucker is. Okay, y'all remember how to do this? Where does 1 go?
Six.
That's the first place 1 shows up, and it's at the tail end, so it cycles back to 4, right? Okay, so follow it from there. Where does it end up? I agree. I think it ends up at 2. 1 goes to 4, no 4, no 4 to 5, to 1 to 2, right? Okay, let's pick up where we left off. Where does 2 go? 1, 2, to 3, to 1. How about that? What's the first number we've encountered that we haven't seen yet? 3, I guess. Where does 3 go?
3 to itself.
Yeah, it does, doesn't it? It goes through itself. Goes to 6, into 4, into 2, into 3. How about 4?
Four.
Goes to 4 as well. How about 5?
6.
Well, I'm not a number, so 6 better go to 5, but I'll check that. 6 goes to 3, to 5. So some people would write this 1, 2, 5, 6. So this complicated transformation, all it does is it swaps out 1 and 2, swaps out 5 and 6, and leaves 3 and 4 alone. How product of cycles. So I'm going to give this to you as a fact. See if you can prove this, or do some examples of disjoint cycles. Then the order of this product is least common multiple of the lengths of the cycle. So what's the order of this thing? This is these are disjoint cycles, right? 1, 2, 5, 6. There's no overlap. The length of this cycle is 2. The length of the cycle is 2. Least common multiple of 2 and 2 is 2. The order of this is 2. For example, if X is, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13, 14, 15, 16. What's the order of this one? Should be the least common multiple of 4, 5, 7, which is 140. So this is an element of, for example, S16, and it takes 140 times to repeat. Think of it this way. The length of this cycle is 4, just 1, 2, 3, 4 by itself. So if you do this twice, 3 times, 4 times, it'll go back to itself, right? Do I agree with that? So every 4 times, this is the identity. Every 5 times, this is the identity. Every 7 times, this is the identity. So in the least common multiple, it should be a grand total of identity, right? This does not work if the cycles are not disjoint, right? Well, if you look at these cycles here, they're not disjoint, and the least common multiple of this is something like 30, but the actual answer is 2, right? So the cycles have to be disjoint. Okay, any questions? Let me give you, I did tell you, didn't I, that the symmetric group is sort of like the grandpappy, right? All groups are contained in the symmetric groups, something like this. Let me give you an example here. We kind of, do you remember how we looked last time at the Pentagon? Dihedral group on the Pentagon? Remember this animal, right? Let me show you how you can use these permutations, and I'm going to show you a magic trick too, which is always good. When we rotate this, remember our basic rotation, we rotated this 2 pi over 5 radians clockwise. What did that do? Where did it take the, if I rotate the 72 degrees clockwise, where does the vertex 1 go to? Where does it end up? It goes to 2. If I agree with that? And where does vertex 2 go? 4 to 5. And the vertex 5 goes to 1. Everybody okay with that? What does flip do? Where does 1 go if I flip it? If I flip it about the y-axis, 1 didn't go anywhere, right? So it's left alone. Do I agree with that? What happens to the vertex 2? It goes to 5, and 5 flips back to 2. Agreed? And the vertices 3 and 4 swap as well, don't they? Now you remember the dihedral relations, right? 5 rotations gives you the identity. Well, let me write E for identity so I don't lose my 1. Notice if you do this cycle 5 times in a row, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. 1 goes to 1 and 2 goes to 2. So it's the identity. Everybody agree with that? If you flip it twice, it's the identity. But does anybody remember what was the big deal? For the dihedral group, you looked at this geometrically last time. Do you remember what happened when we flipped it, rotated it, and flipped it? What happened? Yes.
Was it R-1 and it goes?
That's right. We sort of looked at that geometrically, didn't we? We did this, and then we flipped it, we rotated it, and we flipped it back, and we got that it rotated the other way, right? I don't even have to have a geometric brain to see this because the symmetric group will do this for me. Let's just write this down. 2, 5, 3, 4, and then R is 1, 2, 3, 4, 5, and then flip it again. Now, let's see what this does. I can start anywhere. I usually start at 1, but I'm going to start at 5 for reasons that might, clarity you might see. Where does 5 go? 5 goes to 2, to 3, 4. Where does 4 go? To 3, to 4, 3. Where does 3 go? To 4, to 5, to 2. And where does 2 go? 5 to 1, done. And 1 goes to 2 to 5. Look what we've done. We've rotated it in the opposite direction. And I don't even have to think about it geometrically. The symmetric group just does it for me. So this is a way that we can actually see the dihedral group as a little piece of the symmetric group, right? By the way, how many elements are there in S5? I remember. Say it loudly.
10.
Oh, you're thinking the dihedral group, right? You're thinking dihedral. S5 is 5 factorial, right? In fact, in general, the number of elements in that set is n factorial because it's all bijective functions from n things to itself. This is 120. And the order of the dihedral group on the 5-gon is 10. So yes, you've got this little subgroup, this one right here that is a subgroup of all of S5, and it's just got this little piece in here that does it, which is really kind of nifty, right? Okay, any questions on that? Okay, let's look at some other examples. So this will kind of give you a warm up to, I guess, the next homework. So let's recall first that a field is, we talked about this in the homework, a set with two binary operations. Is a set with two binary operations. That are denoted addition and multiplication. And here's what's going on here. So if you add two things in the field, you get something in the field. The negative of something in the field is in the field, it's associative, and it's got an identity called 0. You also have F with this additive identity removed under multiplication is an abelian. And I want addition and multiplication to play nicely together. A times B plus C is A times B plus A times C for all A, B, C in the field. How many of you have seen the notion of field in a linear algebra course? It may depend on who you've had. Some people do the linear algebra and they only focus on, okay, this is over the real numbers. But some of them might have, probably even in those though, you probably did some stuff with complex numbers, right? Which is another example of field. So standard examples of field, the rational numbers, the real numbers, the complex numbers, Z mod 5, in fact, Z mod P for any prime P. It turns out there are even finite fields. And the order Z mod P is a Z mod P is a field for every prime number P. And in fact, for every prime number P and positive integer N, there is a finite field of that order. It's not Z mod Pn. It's another thing, but they exist, and we might talk about these later. But it turns out if F is any finite field, then the order of F is P to the N for some prime P and some natural number Everybody okay with that? Okay, so. I'm gonna do in this example, something that I think will give you a lot of help on the last homework problem for this coming up week. But first, let me introduce, some matrix groups here. Number one. The empty field. N by N matrices. With entries in F. And in fact, in this case, the matrices, I said they're N by N, but you can actually generalize this. They don't even have to be square matrices. They can be just any size. This is 4. Set of N by N matrices. These are both abelian groups under addition. These are both, because what happens if you add two M by N matrices? What do you get? Another M by N matrix. Everybody agree with that? You can just add them up, just component wise. Everybody okay with that? What would be the identity element if you're going to add up M by N matrices? That's right. It's the matrix that's just full of zeros. Everybody agree with that? And the negative of any M by N matrix is just reverse the sign of all the n's, right? And you probably showed or talked about in linear algebra that addition of matrices is associated, blah, blah, blah. Okay, that's kind of a boring example, but there it is. Right? What about multiplication of matrices? Would I expect these structures here to be groups under multiplication? What happens if you multiply two N by N matrices? What do you get? You get another N by N matrix for sure, right? So you've got that closure thing going on. Is the multiplication associative? Sure it is, right? We're just going to pretend like we remember that from linear algebra, but matrix multiplication is associative, right? What is the identity under multiplication for an N by N matrix? Anybody describe what the matrix that you multiply any other N by N matrix by it and it leaves it alone? What does it look like? It's got ones down the diagonal, that's right, and zeros everybody else. Do you expect an N by N matrix to have an inverse? Here is where the problem lies. Take the matrix of all zeros. Does that have an inverse? Not a multiplicative inverse, right? Anybody remember what's the condition we need on N by N matrices for it to actually have a multiplicative inverse? The determinant has to be non-zero, right? I agree with that. And of course, this one's just right out here. What's the problem with this? I mean, you can't even multiply two things here unless N and M are the same, right? You have to have N and M to be the same to be able to multiply them in both directions, right? Everybody agree with that? So, I don't expect this to be a multiplicative group, but you can have multiplicative groups of matrices. Here's one of them. This is the set of N by N matrices. Over F. With non-zero determinant. This is GL stands for general linear. That's just the notation used for that. But then what I mean is n by n matrices that have a non-zero determinant. Another fancy way of that is saying n by n matrices that are invertible, right? And so I'm kind of saying right out of the gate that these things all have multiplicative inverses, right? Multiply two such matrices, and I get another n by n matrix. And if I have two matrices A and B, how do I find out what's the determinant of A times B? It's the product of the determinants, right? Determinant of A times the determinant of B, right? If both the determinant of A and the determinant of B are non-zero, then the determinant of AB is non-zero. So it's closed under multiplication. And they all have inverses because of this. Let's see why. Those are minus one. Right. Here's another one. With determinant one. What happens if I take two n by n matrices of determinant one and multiply them? I get a new n by n matrix, and what's the determinant of the new one going to be? Also one. Both of these are groups under multiplication. Notice I did not use the word abelian because in general, these are not. If n is bigger than one, I don't expect these groups to be abelian. Let me turn the blade the other way and ask you a question. So these are both groups under multiplication. Do you expect these sets here in 2 and 3, do you expect them to be groups under addition? And what's the problem? By the way, I'll do a sweeping example here. Notice that this one is a subset of this one. Everybody agree with that? Anything that has determinant one certainly has non-zero determinant. Do you agree that both of these matrices have determinant one? So they certainly have non-zero determinant. Do I agree with that? So both of these animals live here and hence here, right? What happens when you add these two?
It's zero.
You get the zero matrix. Does that resulting matrix have non-zero determinant? No. So I don't expect these last two to be closed under addition because that determinant thing doesn't behave very well with addition. Any questions on that? Okay, so I'm going to give you a theorem that goes with this example. Let's see. I want to build. Actually, I'm going to write this in completely. See, theorem, whatever I call this, 221. Let F be a finite field with exactly Q. I'm going to call it Q, but as I noted before, any finite field has to be a prime power elements. These are the n by n matrices with entries in F that have non-zero determinant. I want to count how many elements there are in this group. Any ideas on how to do this? I'm not gonna write the conclusion of the theorem yet. I'm gonna see if we can kind of figure it out. Yeah, ideas on how to count this. This is kind of an interesting learning to count kind of problem. Let's do an example first. Let's do a mirror example. I usually put bars over this, but I'm a lazy man. I'm not gonna do this here. The rule in my field is 1 + 1 is 0. 1 times 1 is 1. 1 times 0 is 0. So this is actually a field because this is in a group under addition. 1 + 1 is 0. So this is C mod 2. And when you remove 0, it's a group because it's only the identity. Do I agree with that? How many of you are computer science concentration or a computer science major? You probably love this field, right? Because it's this binary business, right? 1 + 1 is 0. Electrical engineers love it too. So, and let's let here n equals 2. I want to do this example and generalize it. I want to know how many invertible matrices there are with zeros that I can put just zeros and ones in. Now let's think of it row by row. I need to keep my matrix invertible, so I need to keep that determinant non-zero. Everybody agree with that? What choices do I have for the first or the top row? Think of the top row as a vector, an entire entry. There's only one choice for the top row that screws me up, right? There's only one choice I can make for that top row that there's no way I can get a non-zero determinant now. Anybody tell me what it is? Yeah.
I think a 0 in the left corner.
If I put 0, 0 up here, I'm totally hosed because there's no way I'm going to get a non-zero determinant, right? Do I agree with that? But any other choice will work. So if the only thing that I can avoid, the only thing I have to avoid is 0, 0, how many choices do I have for this first row? Well, I've got the total number of choices I got for this row is I got 2 choices here and 2 choices here. Everybody agree? So I've got 4 choices for the top row, but I can't choose the 0, 0, right? Everybody agree with that? I've got 3 choices here. A grand total of 4 choices take over the 0, 0. Now how many choices do I have for the second row? It might help, linear algebra might help here, because let me ask you this. What's one of the characters? What do you know about the rows in what do you know about the rows in a matrix that has a non-zero determinant? They must be what? Do I remember? The rows must be linearly independent for a non-zero determinant. Everybody agree with that? So really what that means is my second row just can't be a multiple of the first row, right? Everybody agree with that? But whatever this row is, how many multiples of this row are there? Well, you can multiply that row by 0 or by 1, so there's 2 multiples of it. So there should be 4 minus 2. So 3 choices, 2 choices. There should be 6 invertible matrices here. Let's do one more. Let's do 3. Same thing, but I want to know how many invertible 3 by 3 matrices are there. How many choices are there for that first row? Just any choice you can make. 2 times 2 times 2. Everybody agree? So there's 8 choices. Well, what can I not choose for that first row? I can't choose all 0, and there's only one way to do that. So I got 7 choices here. Once I've done this, I have to pick a row that's not a multiple of this, right? Everybody agree with that? And there's 2 multiples of this row. Well, I've got 6 choices for the next. Everybody agree with that? How about this one though? Well, now I've got to pick this row so as not to be a linear combination of the first 2, right? It's got to be something, it's got to be linearly independent, so it can't be a linear combination of the first 2, right? So there's 8 total. How many linear combinations are there of the first 2 rows? 0, 1 times this, 0, 1 times this, there's 4, right? So the number here is 168. There's 168 3 by 3. Invertible matrices over there too. Okay, so how do we do this? Let's see if we can fill in the theorem here. Roll 1. Let's go through this pattern that we've done before. So suppose F has Q elements instead of 2. And suppose we've got a general N here. How many choices are there for the first row of that? Everybody agree we've got N entries here, right? Each of those entries could be filled by any of these Q elements, right? So there's Q to the N choices for the first row. Can't have the 0 row. Everybody agree with that? What about the second row? Well, now I just have to avoid it being a multiple of the first row. Q to the N choices minus how many multiples of this row are there? Well, there's Q elements of the field, that's Q multiples. How about the third row? Well, now this has got to be independent of these 2, right? So there's Q to the N choices again. How many linear combinations are there here? Well, you can, there's Q choices for what to multiply this row by, Q choices this, that looks like Q squared. Y'all see a pattern here? All the way down to so this Q to the N minus 1, Q to the N minus Q, and you just keep counting up your Q powers until you get Q to the N minus 1. Okay, any questions on that? Okay, I'm going to give you just a couple of, any questions? I want to give you just a couple more examples. Actually, I asked you to count the number of upper triangular matrices that are invertible in that group. I think that if you look at this, the upper triangular case is actually a little bit easier. The quaternions. This is one particular example. That my other examples are like more general families, but this is kind of a good small group example of something that's a little bit different. How many of you out there are physics junkies? Right? What? Physics junkies. Anyway, if you like physics, you've probably encountered the quaternions at some point. It consists of these 8 elements. I'm gonna be consistent here on the way that I do this. And here are the relations that govern this. I squared equals J squared equals K squared, it's -1. -1 squares to 1, as you might expect. So these other symbols are just sort of like copies of I, everybody's old friend, the square root of -1, but they have strange relations between themselves. This is a group of 8 elements, and it is often an interesting group to call on if you're looking for, in some cases, some interesting examples of ways things perform. This also will show up, for example, in physics. And I'm going to give you and we have this notion called free group, which we might talk a little bit about later. I just want to acquaint you with this. In a free group, you are given some, I'll call it an alphabet, and a collection of symbols. It doesn't matter what they are, right? X1, X2, whatever. I'll say, and any element of the free group is just a word that you can make. Word using AIs and AI inverse. So, for example, if I had the free group on, if my alphabet is just ABC, the free group on ABC is just every word that I can make using my tools are A, B, C, A inverse, B inverse, and C inverse. Right? Anything I can make. So for example, I might have B, A, C, A inverse, B inverse, A, C, B, A inverse, B, C, C inverse, B, A inverse, A, B minus 2, C, A, C. There you go. Any finite word that I could make using the 3 symbols A, B, C and their inverses is an element of this. Now, I will allow myself 2 ways to shortcut this. If I ever see the same person together, I can call this A squared. C. A, C, B. And if I ever see something next to its inverse, I can get rid of it because this is just the identity, right? So this is the identity, which is sometimes called the empty word, right? So you also assume that if you don't use any letters, you've made the identity. So this is B, A inverse. Oh, look, here's another identity here. So I'll cancel that out. B, B, B minus 2, CAC. And look, two B's and a B minus two. Isn't this my lucky day? So this is B A squared C A inverse B inverse A C B A inverse C A C. And I don't see any other way to make that word smaller. But that's what the free group is it's just, I give you a set of symbols and you make, why is this a group? It's certainly closed, isn't it? Because what happens if I have one word and then another word? I just stick them together and I've got a longer word all composed of that alphabet, right? So it's closed, right? This operation is associative. That's not very difficult to show at all. The identity is the empty word, right? The word that when I attach it doesn't add any letters to it, right? And what's the inverse? Well, the inverse of this one is just build it in reverse, right? C inverse A inverse C inverse A, B inverse C inverse A. You know, just it's the whole, the inverse of any word is just turn around and reverse the exponent, right? Everybody agree with that? So this is actually a bona fide group. Now, sometimes you even have relations on it. I'll give you an example. The dihedral group, as I pointed out when we first looked at this is everything that you can make using the letters R and S, rotation and flip, but I put what's called relationships on it. So remember how the only thing that I could do in the free group is if I saw something next to its inverse, I could get rid of it. And if I saw something next to something like it, I could combine it into a power. Everybody agree with that? This allows me to do more. What this also says is, hey, Jim, if I ever see 5 R's in a row, I can get rid of it. If I see a pair of S's, I can get rid of it. And this also means that if I see SRS in a row, I can replace it by R inverse, right? So this allows me to make my words shorter. And actually, without these relations, this is a very big infinite group. With the relations, it's only got 10 things in it. It's particular reason. Okay, any questions? Any questions? Okay. Let me just give you a quick jump into the world of morphisms. So one of the things that we do in groups is follow. Y'all remember Z6, right? You just add like the clock, right? 3 bar plus 4 bars, 1 bar, and so forth and so on, right? Here's another group. This is under multiplication. 1A, A squared, AQ, A4, A5, and A6 is the identity. So when you get to the 6th power, you start over again and go through, right? So for example, A3 times A4 is what? A7, which is A. Everybody agree with that? These groups are different, right? Because this one's written multiplicatively and this one's written additively, right? But they're different only in presentation, not in spirit. Everybody agree with that? They both kind of got the same thing going on. In fact, really, this thing's functioning sort of like the exponents function here, right? Sometimes we want to unmask groups that have that are the same essentially, or at least have some kind of spiritual connection. And from this, we need the following. This is a big tool in algebra that is used. And morphisms generally in alpha. We're going to call this a group homomorphism. Let circle and H star be groups. I'm going to suppress all the circles and stars later, but I do this here at the beginning of the definition to kind of give us a good feel for this. A function B from G to A satisfying phi of G1 circle G2 is phi of G1 star phi G2 is called a homomorphism from G to H. This is a function from one group to the other, but it's not just any function. Hey, baby, it respects the operation, right? Phi of G1 circle G2, the operation here is phi of G1 with the new operation, phi of G2. It respects the operation as you go from G to H. So it preserves the spirit of the structure. We will talk about the meaning of this with lots of examples next time. Any questions? Okay, don't forget, you got homework to do today. If you got any questions, have a good, this is a long weekend, right? We'll see you on Wednesday.